See, I think with all these rays inside this object in 3 space, diffuse are not constant. I think they range from 0 to pi quarters.
Oh, okay, yeah, you were, okay.
So I do think by far this is the easiest way to represent the order of information.
Is it pi quarters because of the line doodad? It's going to be pi over 4?
Well, I thought the word doodad, yes, yeah. Because I think when you look at the slice or the trace of this 3-dimensional object in a YZ coordinate plane, I'm making a line whose slope is positive 1.
Okay, okay.
That means I do make a 45-degree angle to the positive z-axis.
I just want to make sure.
That's exactly one. So.
Doodad was correct.
Oh no. Oh no, I forgot what's inside the integral. What's the integrand's position? You know, the thing inside the integrand's position. That thing, right here.
Yeah.
Just
So tangent of theta. What else?
Is it y
Rho
correct?
squared. Oh,
No.
rho squared.
Sine phi.
Sine phi.
It doesn't.
And then
B cancel out.
no, it doesn't. It becomes sine squared phi over cosine. Oh no, no, never mind.
Good. Good.
And then you get the r blah 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 blah. blah.
D of that thing.
Yeah, d rho, d theta, d theta.
D theta, D theta.
Oh, okay.
It really is easy if you start at the bottom.
Yeah, maybe you're right.
Yes.
Oh,
Good idea, man.
that was good. That was good.
it's actually supposed to have a little tail going back.
Oh, be quiet. Do you guys mind if I don't finish? How's this integration, right? I'm more worried today about setting this. I only finished the first one just to show you guys I really do get the fourth inspired. And I don't think with these examples I'm throwing on the board today, I don't think they're difficult to integrate.
It doesn't look bad.
No, they're pretty
With the
straightforward.
partial fraction decomposition. just from flying.
Well, maybe if I have time, like I said, I'm going to do these 5 examples, or at least 5 examples I want to make up. What about this?
Is the e supposed to be example or is that?
No, E is a region in 3 space.
Okay.
Oh, by the way, the question is compute its volume using a triple integral in spherical coordinates. Can you imagine what the picture looks like? I gave half it away. The first half is just a cone. So here's my x-axis, here's my y-axis, here's my z-axis. So I think I've got the same darn cone I had in the last example. What about the next geometric figure?
You have to complete the square, that thing.
What does that look like? The sphere of radius 2 shifted 2 units up. So I think if I tack that on, I get something like this. So you guys, I think I've done a poor job phrasing the question. So I'm really asking you to compute the volume above the cone, but below the sphere. So what's contained in the object I have in 3 space on the inboard. And I think I'm looking at a triple integral, where what's in the integrand's position is a piece of cake. It's just going to be rho squared. Happy? You're still not happy. I can't please you anymore.
The tail's starting to go this way, but it should be going a
No,
little
that's
bit.
fine, because it's like
That's fine. Abigail says it's not straight enough.
Bro.
Okay.
What did you say?
Abigail says it's not straight enough.
No, it's
You know who Abigail is?
You mean
Yeah.
Mary Beth Patkill?
No. Her husband, the engineering teacher, he teaches the engineering
Yes.
way, which is a drafting class.
So you insist on vertical?
Huh?
So he insists the tail's vertical?
No. Like, if your line's not straight enough, he marks you all points.
Oh, gotcha. I see.
No, you can't use a ruler. That's the answer. Yeah, the freehand a perfectly straight line.
Jeepers. By the way, my bounds are going to be for row anyways. My bounds are going to be, actually, I don't know. Hold it. Guys, I'm sorry I'm slowing down. Look at this equation. This one right here. My x squared plus y squared plus z squared equals 4z. Sorry, maybe just tired. Let's convert this in terms of rows, datas, and fees. What's another name for this in terms of row? I can't hear you. I still can't hear you.
Don't we have to simplify it
No.
first?
Thank you, I heard that.
Oh.
Equals 4 times z, which is.
Rho cosine theta.
Oh, did you have to look that up?
Sorry, cosine phi. Yes, of course I did. I'm memorized.
Oh, no, remembers anything, just look in the picture. Here's your row, here's your z, and there's my angle phi down below. Clearly adjacent.
Clearly, of course.
Anyway, if I divide both sides by row, which I think I can because my lower bound of integration is going to be 0. I think if I divide by row, I think I get the row is going to be, for the upper bound of integration, 4 cosine phi. Did you guys see it, to be honest?
Wait. For cosine.
Okay, Lisa, you said wait, do this. I have a ray emanating from the origin, so its initial point is at a row value 0. And its terminal point is just tracing out the entire hemisphere.
Okay.
But here's how the hemisphere is described in terms of rows and fees.
Okay.
It's just that I think my theta values will easily range from 0 to 2 pi. My fees easily range from 0 to pi or what? I put together. Yeah, I agree. Here too, you guys, can I beat the clock and not finish? Linda?
Okay, we drew the red arrow.
Yes. So I was just trying to find the extreme values for rows to set up my bound integration for the first inner interval.
Right. How is that, the two shapes, I'm not quite figuring out how to, you have
Okay.
one shape versus the other shape.
Oh, no, that's a good question. You guys, everybody. When I set up the bounds integration, I think I made a mistake. I didn't take into consideration cone.
Yeah.
You don't have to.
I don't think I have to, and here's why.
Okay, that's
Because
right.
I think if all these rays, all emanating from the origin, I think that cone just gives me a boundary value for the phi angle, not for rho. I think no matter where these rays are in red, I think the terminal point is always going to be on the hemisphere, not on the cone.
Because the cone is kind of angling in
It's-
from that equator.
It is, and I think it's
Yeah.
giving me the balance of my phi here.
Okay.
Everything else.
So but don't you have to take into account the circle thing, the half hemisphere thing for rho? Like when you're not rho, but phi, sorry. For phi, don't you have to take into account that when you're integrating?
No, because I think phi is simply the angle I make with versus the axis, with all those arrows.
So it's the angle at which those two things meet. Or it's the
Well, that would be the extreme value. That would be extreme value.
yeah, it's the max value.
But that would be this.
Yeah.
Okay, so
So,
when,
our phi angle is from the z-axis down.
Yeah.
Not from the xy plane up.
Here's the phi value 0. All the way up to the phi value.
you're gonna hit
Yeah, not from the xy coordinate.
I was like, why is it 0 to the power of 4?
So if we,
Patty?
so if we didn't choose the right, the phi value, it would take in the rest of the sphere.
Cynthia, I'm so sorry.
If we did like pi over 2 on phi, so I'm wondering like, there are no points over there, so if you just did it from 0 to pi over 2, it should still come out the same, but it would just do the rest of the sphere. Right? Never mind.
Yeah, I
Ask
see your
your
point.
question.
I see your point. It's just that would take into consideration more volume outside the cone.
And that's why we don't need to really put the cone's equation in, because we've already,
I agree. I just think the cone naturally gives you that upper bound
Yeah.
integration.
so that comes from the cone.
Your
Okay.
row value would have a lower bound if you're doing a sphere.
Yeah.
I think for the whole sphere, my low bound for rho is still going to be 0. Because even with the full sphere here, I think all the rays are emanating from the origin. Their initial point is still the origin. And so this extreme rho value down below is going to be 0. I don't do that much.
Row always start at 0?
Well, no, what if I slid this whole thing up? Yeah, that would be more complex.
What if we had an instance in which row, like the emanating point of row is not constant? Like,
Because it's.
And I think that would be true if I slid this thing straight up.
wouldn't that ask, no, if you slid it straight up, you could make row
What do
two.
you mean not
Because
constant?
the emanating part of row could be two.
Quite the contrary, because this line is no longer gonna be a line with half the origin. I think it's much
So
more
if we're
complex.
looking at.
Okay.
It would be much more complex.
So, let's say to make it more fun, let's say you slide it up and then slide it to the right, and then,
Oh my god.
So say it again.
let's say like to make it more fun, you slide it up, slide to the right, and then like rotate it like 30 degrees. Like,
And if you did that, that would be an example where I think spherical coordinates really don't help. I don't think it's a simplified situation. You guys have to confess. I think with this example, spherical coordinates are beautiful in the sense that whereas you see the equation of the cone with my bounds integration is with rows, thetas, or phi's. Let me ask that again. Where you see the equation of the cone is with the bounds integration for row, or theta, or phi.
Doesn't
How about
it
none
all?
of them? In a sense, you don't see the equation at all. I think so smoothly, the cone just gave me a nice clean bound of integration for the phi values. That's why in this example, I think spherical coordinates is so beautiful. Well, more than that, I think the other bounds of integration were simplistic. That's just one reason. And so when you do that, Matthew, I just think it complicates the picture so much, I definitely would not have gone this direction. I would not have used spherical coordinates.
So real quick about not having to worry about the cone, it's because the cone surface is linear, right? If you had some sort of cone.
Yeah, the cone was linear, and that's really what helped out a lot as well, due to the shape of that surface.
That's right. Is B coming down towards something?
Well, yeah, like my original picture, phi's the angle I make with the positive z-axis. That's why this ray in red going straight up has a phi value of 0, but the one at extreme value phi right on the cone is going to be phi equals pi quarters. Because watch me, guys, because this angle's pi quarters. No, that's not the reason. It's really because this angle's pi quarters. Caleb, you see my point?
Well, again,
Yes.
you have 2 problems, 11 minutes.
Okay. Do you guys remember all that we learned back in Math 31 about moments and
No.
centroids?
Never learned anything about
Moments in 31?
I saw you in 31. I was there.
I was in 30. What's a moment? What do you mean?
I remember the word.
I literally don't ever.
That I don't remember anything about
Okay,
that.
guys.
What is that?
11 minutes. Well, 60 seconds fast, then 5 minutes for 2 problems. You ready?
Okay.
I got a fulcrum and a scale.
Okay.
I want to talk about the fulcrum's location. How about x bar? And let me talk about one particle right here whose mass is m1 and whose position is x1. Let me talk about a particle here whose mass is m2 and whose position is x2. If I'm really to scale here where x2 is closer to x bar than x1, then I think m2 has to be greater in value for the scale to balance out. So to find that x bar position, that center position to balance my scale, I think, well, it's got to be the case. That watch. This distance, which is this, times the corresponding mass of that particle, has to be the same as this distance times the mass of that particle.
This looks strange to like center of mass that we just learned. Like,
That's exactly what it is. This is merely one space. In Math 31, you jumped into 2 space. Today, I'm going to jump into 3 space.
What chapter was this in Math 31? Because I
I'll
don't
show you.
remember this
I'll
at
show
all.
you. To solve for m x bar, let me clear fractions. Let me clear parentheses, excuse me. Let me bring all the terms involving x bar to one side, because I want to isolate it. Let me bring all the terms not involving x bar to the left-hand side, because I'm trying to isolate x bar. Then I think x bar can be interpreted as nothing more than the sum of my x sub I times m sub I, as I range from 1 to 2, to the total mass, which is the sum as I range from 1 to 2, of my m sub I values. I sometimes think of this as the moment, the numerator as the moment with respect to the origin, I sometimes think of this as a total mass of my particle. My particles, plural, excuse me. And that's gonna give me my balancing position.
It's like center of mass.
Exactly. I'm just gonna jump into higher dimensional space. So I think the moment with respect to the well, if it's for x bar, wouldn't that be respect to the?
Could you repeat the moment part and which part?
Yeah, this is a man-made definition of it.
Okay.
I sometimes interpret the sum of the product of the x sub i's with the m sub i's as the moment with respect to the origin. I sometimes think of this as my total mass. But it's a very simplistic system, you guys. I'm merely working in the, sorry, it's slow. I'm working in a one-dimensional system.
Is it supposed to be n?
In n.
A sum from 1 to m, I equals 1 to n.
I went 2 in this case, but it could be n. It should be n with more particles. So the moment with respect to the individual coordinate planes, like for example, how about the yz coordinate plane? Is simply going to be how far I am away from it. That'll give me the x position. And I think this is going to be nothing more than the evaluation of a triple integral times density back in math 3 when density was constant. And since it was constant, from now on, I'm going to let it be a variable expression. And I will think of it as a variable function in terms of x, y, and z.
The density could vary. We could have non-uniform mass.
What did I just say?
It's constant.
I'm sorry, I take that back. I meant to say, unlike math 31, density is no longer constant. Let it vary in terms of where its position is. That's what I meant to say.
Is that a row in x, y, z or a row?
Leave me alone.
Row in terms of x, y, and z?
Yeah, so rho as a function in x, y, and z. In other words, the density relative to where I am in free space is not a constant. And everybody, can I come up with an example? I want to make one up out of thin air. How about this? I could make one up out of thin air. What about the x-axis? The y-axis is the axis. Not that I'm done writing over there. I'm not finished. And let's consider a sphere.
Is this 4?
4 what?
Example 4?
Oh, sure, I guess. But let me consider just a portion of a sphere that's sitting right here in the first octave, whose radius is 1. Let's compute its center of mass. Now, if you open your text, because I'm trying to rush, we're going to have 3 different equations. If you have your book, I want you to open up to section 13.6. Now, I've got 3 different equations to look at, and I'm looking at page 940. Now, if you look at the x bar, the authors express that as a moment with respect to the yz coordinate plane. But technically speaking, that's going to be my density function times how far I am away from the xy coordinate plane. And I'm going to divide out by total mass. And I'm going to compute y bar and z bar just the same. It's just that with respect to the xz coordinate plane, I've got to factor how far I am from the xz coordinate plane, which is going to be the variable y.
Is that another e? Or is that on the bottom part, x bar equals?
Yeah, that's E, Euler's
Oh,
constant.
no. Not that one, not that one. The other one.
Yeah, that's just a big E.
Oh.
But that's uppercase, so you wouldn't confuse that with rho.
I'm sorry, that's an R, right?
What's an R?
No, it's dv.
That's a D. That's a DB.
It's a D square root symbol. You guys, I'm going to start typing on the screen. Just typing.
I'm telling you, Balaguy, it would probably go faster.
Touche. That really hurt. So you guys, again, because I'm trying to skip the time on the clock, these two are only going to change in terms of the variable x is going to be a y and a z, because I think y is my distance from the xz coordinate plane. And the z you see in your text is how far I am from the xy coordinate plane. So to come up with the center of mass of this particular object, you You guys, let me just apply the formulas. Well, again, because I'm thinking that clock, I'm not gonna come with x bar, y bar, and z bar. Let's just set up finding for x bar. And for x bar, the center of mass, I don't know. I gotta give you a row function. Can I make one up out of thin air? Suppose the density at any point within this object is proportional to the square of its distance from the origin. Then I think to find the x-coordinate of the center of mass, I've got, at least in the denominator's position, a triple integral, where my density function is x squared plus y squared plus z squared. Do you guys agree so far? Oh, but shoot, that looks like such a prime candidate for spherical coordinates. Let's rewrite the denominator. I think downstairs in the Enneagram's position, I have, I really have, I can't hear you. I still can't hear you.
Something?
Yeah,
Isn't it gonna be a row cubed?
row
Fourth.
to the fourth.
Why row to the?
Why is it to the
Sine
fourth?
phi.
Oh, never mind.
D rho, d theta, d phi. Oh, shoot, now I gotta worry about my bounds of integration. You know what? For my bounds of integration, I guess I better look at how the row values are changing within this region in 3 space. And having a ray emanating from the origin just to the surface of that sphere, remember what its equation was? X squared plus y squared plus z squared equals 1.
So it goes from 0 to row squared or what?
So it goes from 0 to 1.
Sorry. No.
0 to 1, I agree. My row values change from 0 to 1. They're constant. How do my thetas range?
0 to pi over 2.
Well, theta. Oh, sorry, you're right. I was thinking the whole thing. I said the first octant. I agree with you. And the phis?
0 to pi over 2.
I agree. Now, you guys, I think in the numerous position, there's not going to be that much changes. I think I'm merely going to have a triple integral, same bounds of integration. It's just that on the inside, I've got my row to the fourth, the sine of phi. I'm going to integrate with respect to rho, and then with respect to theta, then with respect to phi. The only thing that's going to change is I got an extra factor of x. Huh. But shoot. X simply has another name of... Hold on, I need more room. You said it's going to be rho.
Sine phi, cosine theta.
So rho, sine phi,
Cosine theta.
cosine theta. Everything inside this big black box simply comes from the extra factor of x. And then I'm sliding over, integrating with respect to rho, then with respect to theta, then with respect to phi. Now, I am not going to take the time to evaluate this integral. But if I did, I'd find the x-coordinate of the center of mass. Now, I think to find the y-coordinate of the center of mass, what changes downstairs? Nothing. What changes upstairs? So cosine of theta becomes sine theta. Now, if I'm going to find the center of mass, the z-coordinate of the center of mass, nothing changes downstairs, but what changes upstairs is that everything in the box now becomes rho cosine of phi. Because that's how I interpret z-coordinates with spherical coordinates. Did you catch that? Did you want me to say it again?
Could you write those 2 other boxes?
Yeah, I think when it comes to y bar, dot, 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 inside my box, that's simply going to change to a rho sine phi times the sine of theta. And when it comes to z bar, what the heck do you see in that box? It's going to be nothing more than z, which I described this way in terms of spherical coordinates. Rho times the cosine of theta. I've never felt so beaten down in terms of my rho's.
Well,
So-
you got 4 out of 5, by the way. So
I looked in the index, and the only place that moments are mentioned is in this chapter that we're working on right now.
So,
Oh, then maybe I stand corrected. I'm just so used to teaching method one.
Linda, you were in there, right? You didn't hear that before we left?
All right, you guys, you know what? I might stand corrected. With the books, maybe it's not in there. I didn't realize that. I forgot any of these. So, you ready for some homework?
not yet.
Not yet.
I mean, I'm sure you have.
So, back in section 13.5, you guys, I'm sorry, late. I said, I need room. Back in section 13.5. I know I already assigned a lot in terms of cylindrical coordinates.
Correct. We need the spherical part.
No, yeah, definitely not done spherical. No
Right,
cylinder.
right. So you ready? So dive in. So 35. To 55, on. Did I sign anything beyond 64?
No.
How about 65 through 69 on? Those look good.
65 through 69 all
Odd.
odd.
Well, you guys are not finished. 13.6. I want you guys to take a peek at the following.
Are you gonna write this down, or?
Well, no, that's why I was hoping to just read it off easily.
I don't know.
So in section 13.6, look at 33 through 38 even. Sorry, 33 to 38 all, excuse me. Man, I don't like his exercises. All right, hopefully that'll be good enough.
What's the quiz on Friday?
The quiz. How about just on last night's homework, which was cylindrical coordinates?
So
In other words, I'm giving you another opportunity for the quiz I just gave back.
the 13.5 stuff that you assigned?
Yes. Yes. Because I think cylindrical coordinates is nothing more than polar coordinates. I'm introducing an extra factor. We're next week mentioning